subscribers and someone who has donated to me in the past asked about this particular concept, teacher-student distillation, and not that like weighs anything into like the videos that I make overall, but when I have like what videos am I going to make, and I'm low on content at the moment. I don't have ideas. Generally, I have ideas, right? So I just go through. But then, like sometimes, every once in a while, it's like, where am I going to pick from? The first place I'm going to pick from is obviously that. So here we go. And so this person asked about teacher-student distillation, and so I give you two examples in this instance. I first built out a CNN model, and then I realized I'm very like kind of biased towards showcasing CNN models on this channel in these instances, and it's because they're simpler to build and train, like flat out. And then so I give you also an example of a BERT model below here as well, and then so swap out BERT for like a bigger model you want, right? But so let's go through here, and then so this is an example of knowledge distillation. The first example is usually using on fashion MNIST for a CNN teacher with a linear student, and a sentiment analysis for the second model with a BERT teacher and a BERT student. This notebook demonstrates knowledge distillation, a technique where a smaller student model learns from a larger, more complex teacher model, and it includes two distinct examples. Part one is the MNIST handwritten digit classification. So, sorry, not fashion MNIST, MNIST handwritten digits. So the teacher model is a convolutional neural network, or a CNN, with two convolutional layers, a dropout, and two fully connected layers. So the teacher isn't a particularly large model in this instance, right? Student model is only a single layer, fully connected network with dropout. That's it. Like the student model is very simplistic in this example and in this instance. And then so we're going to use distillation, and the student is trained using a combination of the standard cross-entropy loss, so hard targets, and distillation loss based on the KL method, divergence between the student's softened output probabilities and the teacher's softened output probabilities. So essentially, we're wanting a convergence of between the student and the teacher, right? Like, so we want them to we're measuring the accuracy between and the loss between those two, essentially as our like second loss rate. And then so, but the softening is achieved using a temperature parameter, so we can kind of like adjust that and give it some fuzziness. And so, baseline comparison, the student is also trained without distillation to provide a baseline for comparison. Part two is the sentiment analysis with BERT. So within this model, we have a teacher-student model. Both are, one is a pre-trained BERT-based uncased model, and it's fine-tuned for binary sentiment classification. And the student model is a smaller BERT model with reduced hidden size, fewer layers, and fewer attention heads. And it's initialized with a configuration derived from the teachers. So distillation, it's similar to the MNIST example. The student is trained with a combination of cross-entropy loss and KL divergence-based distillation loss, using softened probabilities from both the student and the teacher. So like, I want to highlight within this, like I don't have to change the methods between CNNs and NLP models in this instance, which is why I often showcase these things as CNNs, right? But I realize like, man, I showcase CNNs like all the time on this. So let me also do an NLP. So the data set is a small dummy data set, and then it's just like, I'll show you, it's just like really small. I made it myself. And then we utilize Hugging Face transformers within this. Here's key concepts, and let's run through kind of the code here. And then so first one is that we're training this is the CNN model, and then so again, like this is the teacher isn't complex, right? And like that's what I want to point out in and of itself. Like the CNN model is this is a small CNN model for the teacher, and then I'm distilling it into an even simpler model, like one layer, right, flat out. But like it's just like handwritten digits is like 1 through 9 handwritten. So it's like it's not having to do a lot. And then so I have it trained for 3 epochs in this instance, and I have it reduced for collab because it ran for 12 minutes and 30 seconds. It just finished running. And then I have essentially to go through and train the student model with the distillation process. So we'll go through and we'll see the results of that. And then we essentially, this is the code, right? This is how the method, right? This is essentially kind of like this chunk right here. So get students, teachers logits, student logits, distillation loss, student loss measuring the cross entropy, and then the combined loss. So this is like what we're training, right? Like what is getting like injected into the student basically. And it's just like adjusting its weights off of the teacher. Like, a lot of people like want to add more complexity onto these things than they are, right? That's how I look at it personally, honestly. Like, uh, I would like I acknowledge and would say that like I'm a smart individual, but like I'm not like Einstein, you know. And so if I can pick up on these things, then like it's intuitive that like other people in the world would definitely pick up on these things, right? So like I like it's it's these concepts are a lot simpler than you think they are, is kind of the bottom line here, right? And then so you look at this and you might think like there's more to this. It's really not. It's this chunk of code, and then all it's doing is we're just essentially combining the loss from the teacher and the student, and then trying to get them to converge nicely. And that's basically it, right? And then we check the execution here. We're going to see if GPU is available. In this instance, it's not. That's why it took 12 minutes and 30 seconds. Probably would have been like 3 minutes. So I should have done that. And then we train the teacher, train the student without distillation, train the student without distillation is our baseline. And then we go through and like, so what I want to show here, right? So this is the student model. And then so we can see here, I probably could have stopped this after one epoch flat out, right? Because after one epoch of training, what we see if with the, so teacher ends up really nice, right? 96%, and then teacher kind of overfits, like ends up happening, right? I like a teacher should have stopped after one epoch for sure, because it's like loss is down to like 0.007 here, and then you can see it like loss is higher here, ends up higher here, and ends up higher here, lower than this than here, but like epoch 1 was the best, so it kind of overfit, and then we kind of grokked it out, it looks like, and then so test accuracy, yeah, 99%. See, like we could have stopped it definitely like here, and it would have been okay. So like this again, this isn't like this data set, like these numbers, like doing this type of action isn't hard for these models. So I'm just highlighting that. That's why we can use this simple model for this. And then so the teacher gets 99% accuracy up front. And then so we go through, and then we can see like the student is like performing much worse, right? But like as far as the like distillation loss, but like this the student loss goes down. Okay, and then so it's like starts off a lot higher, and then here this is where the teacher ended, right? So here, right? So 0.5 after one epoch, we have the student there. See what happens after that. Ends up higher again. So yeah, and then so like in both instances, we should have stopped these after one epoch, and both these models would have been better, right? So simpler in this instance would have been better. And like if you're dealing with like a simpler scenario like this, you know all of the variables, right? That's like this MNIST fashion, like the MNIST handwritten data set. Like it's handwritten digits 1 through 9. Right? There's like 9 categories, and it's one of the 9 categories. So I know within the data set structure what it's going to be, right? That's why I like that particular data set. And so within that, if you give that a simple problem and like, you know, here's all the categories, 97.2%. So the like, and 97.15%. So teacher ends up 99%, student ends up 97.24%, and then student with no distillation ends up at 97.15%. So distilled student ends up being slightly better than no distilled student, but teacher in this instance ends up being better. But in this instance, teacher ends up being better because of a few factors, right? One is that this is a small student to teacher to student model. 2, this is a simple problem where the teacher is getting 99% accuracy anyway. It's kind of hard to get like to go up from that accuracy, right? That like I would question if the model went up from that accuracy, honestly. So that's kind of how that ends up shaking out. And then so again, I realize that maybe it's just like you don't want to look at CNN models every single time in this instance in my channel. So here's like an NLP model, like an LLM model, right? So essentially a transformer model. We have our sentiment data set, which I'll show you. It's I make it up, and then we're just going through, and then this is all just for the data set itself, and then for the data loaders, and then for the model itself. So you can swap this out. Like that's why I have this built out here. So like if you want to make this like I mean put in like DeepSeek R1, and you could do that, right? If you have the GPU, like if you put DeepSeek R1 in this collab notebook, it'll crash it. But if you wanted to, you can go up to that, and all you would have to do is just swap this model name out. I'm just pointing that out, right? And then same thing, like so. Then you're distilling to the BERT model, but you can just up the quality of the student from here, right? So this is your student model here. So you can see here, it's like a number of heads. We've got 2 heads, 2 layers, and 2 intermediate. And as far as the intermediate size, so you can adjust these up. Like if you've put DeepSeek in here, you can put I don't know, like 12 hidden layers maybe. And whatever you want to up it to, you could exponentially up both the student and the teacher model from here. That's why so scaling, right? Like why I always do these small scale experiments is because there's no point in having to scale up past a certain point. I can scale it to a certain point, and then once I've scaled it to a certain point, scaling models are going to tell me essentially how it's going to function primarily from there. I have a good enough understanding, and then it's significantly more expensive to scale up from there. So I'll just stop the experiment before then, and that's what I do in a lot of these instances. And then then we have our distillation training function. So this is all of this is the student teacher for the NLP model, and it's all of the same stuff that we're doing up on that top one. So it's the distillation loss, the student loss, and the combined loss, all of the same features. It's doing all the same stuff. It's just a slightly different math because we're dealing with NLP as opposed to CNN. But it breaks down. It's literally the same overall functions, right? And then same thing, we're measuring average training loss, average distillation loss, and then average between the models, and then that gives us our second lever as far as our loss lever. And then basically go through CUDA if CUDA is available, and then this is my data set right now. Right? You probably want to change out this data set, but so this is the training text that it has right now. It's just two sentences, basically. This is a great movie. I really enjoyed this. Absolutely fantastic. Or this is a terrible movie. I hated it. Absolutely awful. And then so you probably want to maybe use an actual data set or anything that you want in there. But this is just for simple purposes to get this to actually run in a collab environment for you. If you wanted to actually execute it here and wait the 12 minutes again, I'm utilizing Adam W. So I've been a lot more of my videos, it's been Adam W, right, as opposed to Adam. I'm just pointing that out. Adam W seems to be working out better for me in these instances more and more. And so I'm a fan of Adam W. And then training it for 3 epochs, you can set that to whatever you like. And then there you go. And then so you just train the student with distillation. And then I would expect the same results, or remember, there are instances where the student model can outperform the teacher. I wouldn't expect that in this instance, just being honest. In that instance, and in those instances, what matters is a very good teacher model and a very good data set. Good teacher, good training. Okay, it makes sense, right? And then what we're looking at here, kind of flat out honestly, is garbage teacher, garbage training. Because it's simple examples, right? But we can scale it up from there from garbage to good. This is a F tier chocobo. We can make it a S tier chocobo if we want. We would just have to. It would be a lot more computationally expensive to do so. But so here it is laid out for you. I'll leave a link to this collab notebook in the description. If you'd like this type of content, please like and subscribe. Thank you very much.